Okay, kids, let's do some mirror math. Now, I talk about mirror math a little bit at the end of one of the mirror drawing videos. And I mention it, but let's just go through a couple of full examples to make sure that you are educated on how to do this right so you can do well on the homework and well on subsequent academic adventures that might have you doing some mirror math. All right, so even if I'm doing mirror math, I like to draw things out. I like to, draw things out real quick versions of things. So I'm going to write the problem down. Let's say that I have a mirror. It's concave. Okay, concave. I'm seeing if you can see that. Here you can. Okay, concave. And it has a focal length of 10 centimeters. And we're going to put an object. Distance of the object is at 14 centimeters from the mirror. Oh, that's just distance of the image. Distance of the object is 14 centimeters from the mirror. And then let's go ahead and calculate what's the distance of the image, what's the height of the image, and what's the magnification factor. Let's go ahead and get her done. Now, like I said, I like to draw these out quickly to visualize what's going on, and I would hope that you would do that too. So, principal axis, draw a curvy curve, F, C, F is 10, so C is 20, DI is 14, DO is 14, so it's about there. And then I'd go parallel focus, focus, parallel, and then through the center of the curvature, something like that. And we end up getting an object, or an object here, an image about there. And I draw that out quickly and I go, okay, all right. Now from my image that I've drawn here, from my drawing, my image is, well, let's see, that's 10, 20, 30, maybe it's around on my very quickly done, not skilled drawing, about 30 centimeters away. So I'm going to write that down here. The distance of the image appears to be 30 centimeters. It certainly appears to be larger. I mean, quickly, it looks like it might be about 2 times as large. So if I drew this out to be like 5 centimeters, the image distance looks like, the height of the image looks like it's about 10 centimeters, and it certainly is inverted. So the magnification factor appears, so I'm just doing this by visual, I'm not doing any math, just looking at it. It appears that the magnification factor is at 2 times, because if that's 5, that's 10. So M looks like it's negative 2x. The negative means it's upside down. I'll show you that with the math. All right, so let's go ahead and do the actual calculations and see how close my quick drawing looks with the numbers to what the math says. Okay, here we go. 1 over di equals 1 over f. So 1 over f is 1 over 10 minus 1 over do, which is 1 over 14. 1 over 14. Let's do some sweet 4th/5th grade math. Math was fun. So 1 over di. I'm using 140. Use whatever you want, okay? You say potato, I say potato. So 140 is my common denominator. Okay, 14, 10. I get a difference of 4 over 140, but that's 1 over di. I want di, so switch it. 140 divided by 4 is di. That's going to be 70 over 2 or 35. It should be 35. So the distance of the image should be 35 centimeters according to the map. Now, of course, in my quick drawing, I came out with just a quick analysis looking at it of 30. Let's see. It's not bad. So I'm not too bad. I mean, it's just a quick drawing for crying out loud, okay? Give me a break, give me a break. So there we go, okay, kind of agreeing with a quick drawing of how far it should be. Let's do a height calculation. So height, I'll get rid of this. Height, hi-ho, di-do, hi-ho, di-do. So hi-ho, bring that up, do, and there's ho. All right, so calculate that out. So the height of the image is going to be equal to the distance of the image. The distance of the image we just said is 35. And that's multiplied by the height of the object. Let's say that's 5 centimeters. Why don't you measure it and find out? Because it doesn't really matter. We're getting a comparison here. I mean, if I measure that out, it's probably about 5 centimeters. Actually, let me check out. Check out. Let's see. Here's centimeters. There's a 0 there. It is. There it is. There it is. Okay. Yeah, it's more like 6. So I'm saying 5. So 5 centimeters. And the distance of the object was 14. And so we'll do the math on that. 5 times 35, that's 1, 2, 3, 4, that's 140, 150, 60, 75, 175 divided by 14. 175 divided by 14. I'm not doing that math in my head. And I know you kids at home aren't doing it. You know, you're sitting there drinking popcorn and eating root beer. So 175 divided by 14. You kids relax. You've had a hard day. So 12.5. So 12.5 will be the height of the image. I was guesstimating, I said 10 in my guesstimation. Not bad. Not bad. Close enough for government work. That's what I say. And then last but not least, let's do a magnification. Magnification is a ratio of hi-ho or di-do. So hi-ho or di-do. So I'm going to go hi-ho on this. So M is equal to hi-ho, which is equal to di-do. So you can use either one. I'll go hi-ho. And remember, when it comes to magnification, let's put a negative here, because that's going to tell me if it's inverted or not. If I'm not drawing this out, I can tell if it's inverted or upright by what I get for an answer. So this is going to be hi, 12.5 divided by ho, which I use 5. 5. So our magnification is 2.5. It'll go in there 2.5 times. So 2.5, and it's a negative 2.5. We get a negative 2.5x. I like putting an x in there. You don't have to, but you know that usually means magnification factor. You put x 10 times or 2.5 times. So we get a magnified image. 2.5 times is great. Of course, in my guesstimation, I said 2. The negative means it's upside down, and that's why it's important to have the negative there. So it tells you if it should be upside down or upright. All right, so now, like I said before, you might say, well, you're always going to get a negative. No, you won't. Okay, let's do one where you won't always get a negative. Let's do another one. So this time I'm going to do one where we have a convex mirror. So we're shifting to convex mirror, and I'll keep the numbers here the same. I'll use the same numbers, focal length 10 and the object 14. Okay? So at convex, what happens this time? Well, go ahead and draw it out, just like we did before. Don't change anything, just because it's convex, draw it out the same. So this is 10, that's 20. Distance of the object is 14. We put it here before because it was a concave mirror. This is convex. Convex is bubble out. So the object is on the other side. The object is about 14 is about, yes, but right about here on this side. And I drew that probably about 6 centimeters or so high. It doesn't matter. Draw it however high you want. And then let's go ahead and do a quick drawing. Okay, parallel, doink, guided by the focus, toward the focus. Doink, bounces off parallel. And I have a center of curvature line I can draw. I'm not going to draw it. As I've said before, you only actually need 2 lines to get an image. So we're going to keep it there. So it's not as messy. Okay? It's not so Lionel. Lionel Messi. It's funny. It's funny because that's a soccer joke. That's a yeah. Oh, thank you. So now I'm going to draw back the reflected rays. That's a reflected ray. This arrow here is a reflected ray. I draw those back, and they intersect about here. So I get an image that looks like it's about half as high. I get an image that looks like if that's 10, it looks like it's around 6. 5, 6, 7, somewhere around there, away from the mirror, and it is upright. So let's go ahead and do the math and see what the math says. All right, so the math, let's get the distance of the image. 1 over di equals 1 over f. Now, 1 over f is 1 over 10. However, muy importante, if you listened to the end of that video, maybe you didn't, maybe you got bored and shut it off. Okay? If you listen to the end of the video on mirror drawings, I mentioned this, that if it's a focal point in the mirror, this is convex, this is outside the mirror, this is inside the mirror, it's negative, it's virtual, it's negative. You have to put a negative. If you get an answer that's negative, it means the image appears in the mirror, and that happens. Negative is virtual. So go ahead and put a negative there. You have to do that with a convex. Convex mirrors are also called negative mirrors. They're called convex, okay, bubbling out like that. They're called diverging because the light diverges. And they're also called negative mirrors because of this exact reason, because you need a negative focal point. So minus 1 over 14. Again, I'm going to use 140. Negative minus 140, that's 10. That's 14. So what do we get? Negative 14 minus 10 is negative 24. Over 140, flip that. So 140 negative 24 on the bottom. So we get 140 divided by negative 24. And that will give me di when I do this out. So 140 divided by 24 is 5.83, but it's a negative 5.83 centimeters. Oh, that's almost perfect. Nailed this one. Earlier I said that looks like it's between like 5 and 6. Boom, 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 boom. All right, so we've got that down. Now this negative means it's virtual. You haven't done the math wrong. It means it's a virtual image. So that right there, the math can tell you it's virtual. It's also virtual because it's on the opposite side of the mirror that the object is. That's virtual. Object, image, opposite sides, virtual. All right, we'll do a height calculation. So hi is equal to hi ho, we put the ho over here, di do. So distance of the image, we just calculated distance of the image, negative 5.83. Distance of the image. Distance of the object was positive 14. I get my numbers right here. The image was negative. We just calculated that. The object was 14. So hi ho equals di do. I need the height of the object. The height of the object has to go here. I'll once again call that 5 centimeters. It looks like it's a little bit bigger than that, but it's good enough. 5 centimeters. Okay. So go ahead and do the math. When you calculate this out, okay, we will get height of the image will come out to be 5.83 times 5, enter, divided by 14, enter. 2.08. We'll call it 2.1. It's a negative 2.1 centimeters. That's the height. Okay, now that's reduced because if that's 2.1 and I used 5. So we have a reduction. We have a magnification factor is less than 1. If we do the magnification, let's do the math. Let's figure it out. So I'm moving this out of the way. Let's do the magnification here. So m equals negative hi ho. Negative hi ho. Negative hi negative 2.1. Okay, negative negative positive over 5. So if I divide that out, I'm going to get about 0.4, slightly off that, but about 0.1. It's going to be a positive value about 0.4, but let's get an actual retail price here. Divided by 5, 0.42. So positive 0.42x. What does that mean? Positive point something means it's smaller. It's smaller by more than 2 times. It's less than half the original height. So it's reduced. It's reduced. And it's upright. Positive m means it's upright. We have an upright image. That's what the positive here means. Okay, so there's a couple of examples of doing the math through, showing you that you can use a negative focal point, have to if it's a convex mirror, and you can get negatives, and that's okay, because that just means they're on the virtual side. Okay, I think we'll make like a gift and wrap this one up, and see you on the flip.